In this lecture, which covers section 2 of chapter 7, we'll talk about binomial random variables. We'll define what a binomial random variable is. We'll talk about how to handle dependent events. And we'll talk about how to find the center, the spread, and the shape of both the counts and the proportions. We'll wrap up by talking about using the normal curve to approximate. In the 4 stages of statistics, we're talking about probability and binomial random variables. To review, remember that a discrete random variable is one that takes a finite or countably infinite list of possible values. Later on, when we're doing inference on categorical variables, we'll be interested in looking at the proportion. We'll start by looking at counts, which is discrete, but eventually we will pass to proportions, which will be continuous. A binomial random variable is a variable that meets several conditions. First, it has to be a count. Binomial random variables count things. Usually we'll call those things that it counts successes or wins, something like that. So we're counting sampled individuals that fall into a particular category. In other words, we're counting our wins. But we have 4 other criteria. First, the sample size is fixed. Second, each selection has to be independent of the others. Third, there are just 2 possible values for each individual. That's why we often talk about winning versus losing or success versus failure. And each individual has the same probability of falling into the category we're interested in. Let's take a closer look at these 4 properties. Let's say that the random variable x counts the number of times we see tails when we flip a coin twice. Why is this binomial? And what are n and p? Well, in order to be binomial, it has to count something, and this does. The sample size, which is n, has to be fixed, and it is. We're flipping the coin twice. Each selection has to be independent of the others. They are, because the coin doesn't remember what happened before. On the second toss, heads and tails are equally likely. Are there just 2 possible values of the variable that we're counting? Yes, we're looking at heads and tails. And finally, does each have the same probability? Yes, 1/2 for both. Therefore, this is a binomial distribution. N is equal to 2, and P is equal to 0.5. So, for the binomial random variable x we saw in the last example, how do we display it? Well, the best way is with a histogram, which is the ideal way to show or to display any discrete random variable that has a finite number of possible values. On the horizontal axis, we'll list out all the possible values for x, and on the vertical axis, we'll indicate the height of each bar using probability. Now, let's look and see some other examples of discrete random variables that may or may not be binomial. First, let's say that you pick a card from a deck of 52, put it back, and then pick another one, and so forth. We'll let x be the number of cards picked until you see an ace. Is this a binomial random variable? It is certainly a random variable, but it's not binomial because the number of trials isn't fixed. We stop the process when we see an ace, so sometimes we might pick 2 cards, sometimes we might pick 7 cards. Let's look at a similar situation. Here we're going to choose 16 cards without replacement from a deck of 52 and let x be the number of red cards picked. Is this a binomial random variable? Well, no, This time, unlike the last example, we do have a fixed sample size. We're choosing 16 cards. But because we're doing it without replacement, these choices are dependent. What about this one? Here we'll pick 16 cards with replacement, so we don't have to worry about dependence, from a deck of 52. Let W equal the number of clubs, X the number of diamonds, Y the number of hearts, and Z the number of spades. And we want to show how frequently each suit is picked. Are these binomial random variables? No, because each individual that we're studying has more than 2 possible values. In fact, there are 4. Now, let's say that we're choosing with replacement from a German deck of 32 cards, and then from a standard deck of 52, back to the 32, back to the 52, etc., to pick 16 cards, where X is the number of aces selected. Is this a binomial random variable? Well, because the probability of an ace changes from deck to deck and from choice to choice, P doesn't stay constant. Therefore, this is not a binomial random variable. Now, let's pick 16 cards with replacement from a deck of 52, and we'll let X represent the number of hearts picked. Is this a binomial random variable? Well, here N is fixed at 16. We're drawing with replacement, so the selections here are independent. We're just counting the number of hearts picked, so each card is either a heart or it's not. And P is fixed for each choice. All 4 of our criteria are met, so this is a binomial random variable. Let's look more closely at this requirement that the selections be independent. This creates a problem for us. Generally, when we're choosing samples, we do so without replacement, which means the choices are dependent. In order to use the theory behind binomial random variables, our choices must be independent. So, recall that we mentioned in the last video that as long as the population is at least 10 times the sample size, we'll call the samples approximately independent. As long as our selections are approximately independent, using the rules for binomial random variables will give us a very good approximation. Here's an example. The proportion of Americans who are left-handed is 0.1. Of the 44 people who have served as president, actually it's only 43, but we'll count Grover Cleveland twice, 7 of them have been left-handed, which is a proportion of 0.16. Now, the question that we might be interested in is, since that proportion, 0.16, is quite a bit larger than the overall proportion of 0.1, can we say that being left-handed people are more likely to become president? So what we'll do is we'll look and see if that 0.16 is unusually high when we're choosing random samples from a population of the same size. So how do we solve binomial problems? One way is to use the binomial formula or use tables. The formula is pretty complicated and tables are unwieldy, so as long as our sample size is small, it would be okay, but our sample sizes may not be. Another thing we could do is use software, use Excel or use our calculators. Later on, we'll see how to do that, but for now, that's not going to work for us. We could use the normal approximation for the count, but I'm more interested in proportions. So maybe we should use the normal approximation for proportions. This is what we're going to focus on. But in order to use the normal approximation, we need both the mean and the standard deviation. So, based on long-run observed outcomes, we can say the probability of being left-handed is about 1/10. Now, let's choose a random sample of 100 people. On average, how many left-handed people should we see in our sample? What should the proportion be? Well, on average, we would expect to see about 1 in every 10 people being left-handed, and there are 100 people total, so that gives us a count of 10. If we convert that count to a proportion, we get 0.1, which is the same as the proportion in the population. So, how do we compute the mean and the standard deviation for both counts and proportions? If x is a binomial random variable, where n is the size of the sample and p is the probability of success, then the mean is n times p. The standard deviation is the square root of n times p times 1 minus p. These are formulas you'll need to know. To convert x from a count to a proportion, we divide by n. So the mean is p, that's the proportion in the population, and the standard deviation is the square root of p times 1 minus p over n. Now, that happens to be what we get if we take the formula above and divide it by n. I recommend that you just learn both of the formulas, one for count, one for proportion. Finally, don't forget that formulas using standard deviation require our selections to be independent. So the size of the population has to be at least 10 times the size of the sample. So, in our left-handed example, with 100 people sampled at random, we expect to see 10 people in the sample being left-handed. The standard deviation would be the square root of 100, that's n, times 0.1, that's p, times 1 minus 0.1, that's 1 minus p. That reduces to 3. How do we interpret those two numbers? Well, in a random sample of 100 people, we would expect to see 10 left-handed people, give or take 3. Sometimes we'll see more, sometimes we'll see less, but overall we'd expect to see 10, give or take 3. Converting to proportions, we would expect to see in our sample of 100 people a proportion of 0.1 left-handed people and a standard deviation, again using our formula, that's the square root of p times 1 minus p over n of 0.3. So how do we use those numbers? Well, the interpretation is, on average, if we choose a random sample of 100 people, we would expect the proportion of left-handed people in the sample to be 0.1, but sometimes it'll be bigger, sometimes it'll be smaller. We'd expect it to be more or less 0.03 from 0.1. So if we got a sample proportion of 0.2, that would be unusually large, because that's more than 3 standard deviations above the mean. Let's consider now the proportion of tails seen when we flip a coin n times, where n is 1, n is 4, and n is 16. Take a look at the standard deviations for these situations. Since we're talking about coin flips, in each of these cases, p will be equal to 0.5. So the standard deviation when n is 1 would be the square root of p times 1 minus p over n, which is 0.5. For n equals 4, the standard deviation is the square root of 0.5 times 1 minus 0.5 divided by 4, which gives us 1/4, 0.25. When n is 16, we'll replace that 4 in the denominator in the previous one with a 16. And when we multiply out and take the square root, we get 0.125. There's an interesting pattern here. At each step, we multiplied n by 4. And the result was the standard deviation got divided by 2. That'll happen in general. Every time n goes up by a factor of, let's say 9, the standard deviation will be cut by a factor of 3. That's the square root of 9. That's what happens with the n in the square root of the denominator. So in general, as the sample size goes up, the standard deviation for the sample proportions will go down. Now, what do these distributions look like? Both count and proportion for a binomial random variable will have a shape that's approximately normal as long as the sample size is big enough. We'll talk about exactly what big enough means in a moment. This is due to a theorem in the theory behind why all the statistical methods that we use works, called the central limit theorem, which says that as n approaches infinity, the distribution approaches the normal curve. It's important to know that if n is fixed, then the shape of the distribution for both count and proportion look exactly the same. Let's look at an example. Let's let x count the number of times we see tails when we flip a coin once. In this case, the two histograms, one, the one on the left, for count, and another, the one on the right, for proportion, these look exactly the same. Notice that the possibilities for the count of tails that we see in one coin flip are either 0 or 1. That also happens to equal the proportion that we could see in one coin flip, either 0% or 100%. What can we say about these distributions? Well, the bars are completely even as we go from left to right. So we might say they're flat. We had another word for that. That was uniform. And they are symmetric. And notice the shapes are exactly the same. Let's jump to 4 coin flips. On the left, you see the histogram for the count of tails we see in 4 coin flips. In this case, the mean is 2 and the standard deviation is 1. On the right, you see the histogram for the same situation, but now we're looking at the different proportions. So here the proportions are going from 0 to 1. The mean is 0.5. Notice that represents a count of 2. And the standard deviation is 0.25, which corresponds to a count of 1. That's why these two distributions look exactly the same. How do they look? They're unimodal and they're symmetric, and except for the scale on the horizontal axis, they're exactly the same. Let's jump to 16 coin flips. This time, we're only going to look at the proportion, which is what we're going to be interested in when we shift to inference. Here's the histogram. What's the shape? Well, that red curve represents the normal curve, and the histogram for the proportion of tails is pretty close to it. We might say that it's approximately normal. Here's an experiment that allows us to flip coins very quickly. Each trial will flip these set of 100 coins once. The probability of getting heads is 50%. The probability of getting tails is 50%. So, if we flip all 100 coins, we are looking at the tails and the heads pop up as they go. What we'll see is, as we scroll down, there's our 1. There were 56 heads. That means there were 44 tails. Now that took a while. So what I want to do is push this button that's going to do another 10 samples of 100 coins each. So we're going to flip 1,000 coins. This is going to go much faster. And there are the results displayed on a histogram. We see a couple of them happen more than once. If we scroll down, we might see you see some of these are twice as big as others. The ones that are twice as big, that means they happen twice. And you can see the counts over here. Here X, this is counting the number of heads we saw. It looks like we got, what did we see twice? There's a 46 twice. On trial 11, we saw it in trial 2. 55, that's the other one that happened twice. Now let's do this another 100 times. And another 100 times. Heck, let's do it 10,000 times. What do you notice is happening to the distribution as we run this trial? What's the shape looking like? Do you see that the longer we go, the more times we run the sample, the closer this is looking to a normal distribution? In fact, we can display exactly what theoretically the probabilities exactly are for seeing each of these values. And you can see it overlaid in blue. Now certainly some bars are higher and some bars are lower, but overall the shape is pretty close. And boy, that looks really close to the normal distribution. Now let's go back to our example about lefties. Here's what we would expect to see expressed as proportions if we choose a sample size of 1. There's a 90% chance that we will see a proportion of 0, and a 10% chance we'll see a proportion of 1. What's the shape of this distribution? Well, it's really heavily right skewed. Let's jump to n equals 16. Here's the histogram for choosing 16, a sample of size 16, where the probability of being left-handed is 0.1. What's the shape of this one? Well, it certainly looks more normal than the last one, but it's still pretty heavily skewed to the right. Let's jump to a sample size of 100. Here's the distribution. That looks a whole lot more normal to me. You might be concerned, somewhat, about the fact that it seems like there's a little bit more of a tail out here to the right. I'm not too worried about that because there is a tail back here to the left. There is nice symmetry. And overall, this looks normal. If you were to just cut off this part of the graph on this side and look at what's left, that would look almost exactly normal. And the part that we're cutting off is very small. So we've said that as long as the sample size is big enough, the distribution of our binomial random variable looks approximately normal. So how big is big enough? Well, certainly it depends on the size of the sample, but it also depends on p. Remember that p is the proportion in the population, or the probability of success. Here's our rule of thumb. The distribution will be approximately normal as long as both n times p and n times 1 minus p are greater than or equal to 10. What this means in practice is that if p is close to 0 or p is close to 1, n has to be quite a lot bigger. That's because as p gets close to 0 or close to 1, the distribution becomes skewed to the right or skewed to the left, respectively. N has to get correspondingly larger to make the distribution look more normal. We saw that in the last example when we were looking at samples of different sizes for the lefties. Another way to think about these requirements is remember that n times p is the average of the counts. It's the number of expected successes in our sample. Similarly, since p is the probability of success, 1 minus p is the probability of failure. So n times 1 minus p is the average number of failures. So we'll say that a binomial distribution is approximately normal as long as both the average number of successes and the average number of failures is greater than or equal to 10. Let's look at some examples using this rule. Here we're going to be looking at sample proportion for several different choices of n and p. To make it easier to see, the alternating choices are in blue. So we've got 5 altogether. Will we say these are approximately normal? So for the first one, where n is 4 and p is 0.5, we see that n times p is 2, and that's less than 10. N times 1 minus p is also 2. If n is 20 and p is 1/2, this is barely qualifying for our rule of thumb because both n times p and n times 1 minus p are equal to 10. Remember, we need those products both to be greater than or equal to 10. If n is 20 and p is 0.1, this is not approximately normal because n times p is 2. Now, n times 1 minus p, in this case, is 18. And 18, which is n times 1 minus p, that is greater than or equal to 10. So that one works, but we need both of them to work in order for our rule of thumb to tell us that the distribution will be normal, or approximately normal. Similarly, if n is 20 and p equals 0.9, we've got exactly the reverse situation. So the distribution for n equals 20 and p equals 0.1 will be very strongly skewed to the right. This one, where p is 0.9, will be very strongly skewed to the left. Finally, if n is 100 and p is 0.1, that's just big enough because n times p is 10, n times 1 minus p is 90, and both of those are greater than or equal to 10. So notice that when n was equal to 20 and p was equal to 0.1, these were not approximately normal. But when our sample size got big enough, up to 100, that was barely big enough. And the bigger n is, the more normal this will look. So back to a question we asked earlier. If the proportion of Americans who are lefties is 0.1, what is the probability? That's what we see here after consider. What is the probability that the proportion in our sample is greater than or equal to 7 over 44, which is 0.16, if our sample size is 44? Now, can we use our normal approximation in this case? Well, no, because the rule of thumb isn't satisfied. N times p is 4.4, which is quite a bit less than 10. Now, we can use some other techniques to actually compute the probability that we see this. And it turns out it's about 0.15. If you use the normal distribution, using the mean and standard deviation calculations we saw earlier, the normal approximation will return a probability of 0.1. Notice how different these two numbers are. Now, it's easy to convert from a count to a proportion and from a proportion to a count, as we need. In a sample of 87 assaults on police, 23 used weapons. 0.44 in a sample of 25 bankruptcies were due to medical bills. So looking at these, what are n, x, and p hat? In the first, n, that's the size of the sample, is 87. X, that's the count that we're interested in, is 23. So the proportion in the sample, p hat, is 23 over 87, which is 0.26. In the second example, we're given p hat, the proportion, and n, which is 25. So we can compute the count by multiplying. The count is 0.44 times 25, and that's 11. So to wrap up, we defined a binomial random variable and listed the 4 requirements for a random variable to be considered binomial. And we looked at several examples where those requirements fail. We talked about how we can get around the requirement that the selections in a binomial random variable must be independent. We talked about converting from binomial counts to proportions and vice versa. We talked about the mean of each of those different expressions of the binomial random variable. And we looked at the formulas. The mean for count is n times p. The mean for proportions is just p. And we talked about the standard deviation. The formula for those were the square root of n times p times 1 minus p. That's for count. And square root of p times 1 minus p over n for proportions. We also talked about the different shapes that the distributions could take. In general, as n gets bigger, the distributions look more and more normal. We talked about when it is in fact appropriate to use the normal approximation to a binomial distribution.